All right, ladies and gentlemen, welcome into sort of a special video here today. As promised in lecture today, I'm going to do actually two examples in this video. The first is from slide 8 of the notes, which is on kind of bearing stress, normal stress, and shear stress in a certain tie rod kind of situation. So that's page 8 of the notes. And then I'll also do one from, I think it's page 10 of the notes, which is a little bit later, on stress on an oblique plane. So we got two examples in this video. So we'll head and go through them now. I'll transfer over to the writing pad and we'll just get right into it. Okay, so on your screen here now, you should see the example problem. This is from, like I said, slide 8 of the notes. This is lecture note set number 1. If you want to sort of take notes by hand by yourself, you can go ahead and, the beauty of YouTube here, pause the video if you'd like to copy this down for yourself. Otherwise, I'm just going to get right into it. So let's start with sort of describing the problem and what's going on here. We have a steel tie bar used to carry 125 kilonewtons of tension bolted as shown. So we have sort of this tie rod here connected between these two different bolts. And this guy is said to be in tension, right? So this bar here is experiencing 125 kilonewtons in tension. So being pulled between these two different bolts. And that's going to influence sort of the size of the tie rod that we need to make sure that it doesn't fail according to the stresses that we have. So it's to be made of 20 millimeter thick steel, okay, which is nice to know. We see that in sort of the diagram of the tie rod here, that the thickness is given to us as 20 millimeters with the following maximum allowable stresses. Okay, so here we have a maximum allowable, this is axial stress of 175 MPa. Here we have a maximum allowable shear stress. So this is shear. And then a maximum allowable bearing stress of 250 MPa. Okay, so this is more of like a design problem where we're given our maximum allowable stresses, and that's going to inform the dimensions of the tie rod that we're going to sort of need to make sure that we don't exceed any of these stress values. So given those maximum stress values, we want to determine what is the required bolt diameter D, the required tie diameter B, and the required width of the rod H. So we have H here, which is the width of the rod. We have D here, which is the diameter of the hole or the diameter of the pin, however you want to think about it. And then B here, which is sort of this full diameter incorporating both the pin and the tie rod material itself to make sure that we don't break. All right, so let's go ahead and get right into it. I think the easiest way to start this is to actually investigate what's going on kind of far away from the bolt in the middle of the tie rod, which is where we're going to have to define that variable H. I think that's the easiest place to start. So let's go ahead and get into this. I'm going to scroll down here. So first, we'll look for H. Okay, and when I'm thinking about H and thinking about this guy being in tension, I want to look at a free body diagram, tie rod, cut in the middle. So more or less I have a situation that kind of looked like this, where I have the tie rod bolted on either end. This guy has some pin or some bolt that's holding it together. And this is under 125 kilonewtons of tension. So there's a pin here that's pulling it this way and this way, both 125 kilonewtons. Okay, and to investigate the dimension that I need sort of throughout the middle of the rod, I'm going to make a cut kind of in the middle of the rod. So we'll cut kind of like right in the middle here, and we'll investigate that portion of the rod, and that's going to inform the dimensions that we need. Okay, so in middle of rod, you'll have this situation going on here. We've cut through our material, and so we're going to just look at one half of this tie rod that looks like this, and we have sort of the hole on the left-hand side, and we've got the pin that's kind of applying this 125 kilonewtons. All right, so in order for equilibrium to hold, so if we say sum of the forces X equal to 0, to hold, we have to have something that's happening at the portion where we cut that sort of balances it out. And I think it's pretty easy to see here that we're going to have some normal force in here that balances this out. And I'm just going to straight away say that we can understand what that is by some of the forces in the x direction equal to 0 is that this is going to be 125 kilonewtons, or going to be required to be 125 kilonewtons for this thing to be in equilibrium. Okay. And when we're thinking about this internal normal force inside of a structure and how much that structure needs to hold in terms of that load, you're thinking about that normal force divided by the cross-sectional area of the piece. And so you should be thinking this load is held in axial stress. Okay, and that looks something like sigma here is this normal force N over the cross-sectional area of the rod. So this is a portion where we're looking at sort of the normal force inside of the rod. All right. Now, in the center of the rod, we kind of were given some dimensions and needed to solve for others. So particularly if this is like the cross-section of our rod here, right, if we're kind of looking at this dimension here, we would say then that the area, or the cross-sectional area of this rod looks something like 20 millimeters times the height h. All right, so this is going to be the cross-sectional area that we use to sort of calculate our stress. But we know that max normal stress, or what I'll call the normal / axial stress, they're kind of like an interchangeable name there, is given to me in the problem up above of 175 MPa. It's like the maximum allowable axial stress for this piece. Right? So that's the case, is 175 MPa. So if I kind of put these two guys together and also include that the area is something like 20 millimeters times the height h that I need, put these guys together and say, then the stress is normal over area, kind of becomes 175 MPa is equal to the normal force, which I know, 125 kilonewtons. And this is divided by the cross-sectional area. The thickness I know is 20 millimeters. I'm going to write that in meters. I just like working in meters. This is 0.02 meters times my variable h, which is the height of the tie rod that I need, or more or less the width of the tie rod that I need to make sure that we don't exceed the maximum stress. So you can do algebra to kind of work this. Remember, MPa is like 1 million pascals. So kind of the left-hand side of this equation is 175 million. If you're working in standard units, 125 kilonewtons, this is 125,000. You're kind of plugging that into your calculator. And so you can work this to solve for h, and you'll find in this case that h is going to be equal to 0.0357 meters, or 35.7 millimeters. That's kind of the first portion of the problem. I think probably the easiest part of the problem that we have. So nothing about bearing stress because we're not really at a pin or a hole. Nothing about shear stress because we're not, again, at a pin or a hole. So we're just looking at sort of the core center structure that's under axial loading, the most simple type of loading that we have in this class, and using just force divided by cross-sectional area. And knowing that it has to be 20 millimeters thick, we can sort of uncover that the height is 35.7 millimeters. Okay, so you can plug that in the calculator for yourself and make sure that I got the number right. Okay, let's move on to other portions of the problem. Next, we're going to look at the required bolt diameter and the required tie diameter. And both of these guys have to do with where the pin and the tie rod are sort of interacting with each other. We're going to look solely at the left-hand side, but you know, there's a portion on the left-hand side and a portion on the right-hand side where we kind of have to make this the same on both sides, but okay, so be it. And these two dimensions are going to be influenced by several things. When we think about the shear stress, that is how much shear can I hold in that pin before that pin breaks. So the shear stress really has to do with the bolt diameter. And then we have a bearing stress, where the bearing stress again has to deal with the diameter of this tie rod. So let's kind of investigate this portion of the assembly. Okay. And let's start by just looking at that diameter of that hole. Okay. So for hole diameter, we have to really consider two stresses. The shear stress and the bearing stress. And let me explain why that is. Okay, so let's look at the pin, for example, or the bolt that they call it in this case. So let's look at a free body diagram of the bolt. All right, in this case, we have the bolt that is here at A, and it's kind of being pulled by the tie rod, right? And this little flange here, which is this gray flange, is sort of resisting in double shear this load that we're applying, which is our 125 kilonewtons on that pin. So if we're going to look at what that bolt looks like, it's going to look a bit like this. So here's kind of a section of my bolt. Okay. And I'm going to put some like marks in here to sort of show where the tie rod would interact with this thing and where sort of the flange would interact with this thing. So I know that the tie rod is kind of like pushing on this left-hand side of that bolt with 125 kilonewtons. And that the two flanges that support this tie rod on either side will resist the pin from sort of moving in that direction. And because this is a case of double shear, that case that we talked about in class today, those loads, in order for equilibrium to hold, will have to be exactly half of the 125 kilonewtons. So this is 125 over 2, and this is 125 over 2. Or, if you do the math on this, 67.5. So this really is the free body diagram of the bolt as it's interacting with the tie rod and the two flanges that are holding it and stopping it from moving. Right. So this is the situation for the bolt. And now I want to know, all right, well, what's the shear stress inside the bolt? Because when we talk about this single shear, double shear situation, we really have to worry about that bolt actually rupturing. And so we want to look at what's the shear stress inside of this. And the easiest way to do that is to cut through this guy, maybe like right above where the tie rod is loading and where the flange is loading this bolt. And so if we make a new free body diagram, we're going to have something that looks a bit like this. Again, the same idea. Got this bolt. And now this is being cut here. So here's our cut. And we have the 125 over 2 kind of on the top side of that bolt. And then the bolt itself has got some, circular cross section here that you sort of can't see that is resisting that 67.5 internally. It has this internal shear force, which I'll just label as capital V, that must balance this out and be equal to 67.5 kilonewtons. This is the internal shear force inside of the structure that must exist to balance out that 67.5 that the two flanges are applying to it. Okay, so this load V, this guy here, acts on the cross section of the pin. So if we think about that circular cross section right there, that shear load V is acting on that circular cross section of the pin. And so because of that, the shear stress in the pin is, we know from class, this shear load that must be held internally in the structure divided by the cross-sectional area of the pin in that location. No problem, right? That cross-sectional area of that pin can be no larger than the hole in the tie rod that we have. So we have a hole in our tie rod right here, this hole right there where our pin is going to go, and the pin can't be bigger than that. So that means that the diameter of the hole of the tie rod must be at least the same size, if not bigger, than the pin that we need. Okay, so we can use the variable d as the diameter, which influences the area here of the pin, right? And so if we say that this pin has a cross section or a diameter of d, then the cross-sectional area of the pin is just pi d squared on 4, or pi r squared, however you want to think about it. And with the constraint of the shear stress must be less than or equal to the maximum allowable, which here we're told that the maximum shear stress allowable is 100 MPa. So I'll just say that it's going to be equal to 100 MPa. We can also put these two little pieces together, where remember this is pi d squared on 4. This will help us determine what variable d that we need for that tie rod diameter. Okay, so here we go. Tau is the shear load on the cross-sectional area. Let's put numbers in here. It says 100 MPa. This is equal to the shear load, which is 67.5. Remember, that's from sort of up here above. Kilonewtons. And then divided by cross-sectional area, which I'm going to use that variable d. It's pi d squared on 4. All right, put this all together, and you'll come up with the diameter of the hole must be at least 28.2 millimeters. All right. There we go. That is the diameter that we require such that the pin does not fail in shear. Okay, important. But that diameter d doesn't just influence the size of the pin. Okay. We also see that variable d coming through in the bearing stress. So not only do we need to check the diameter because of the failure of the pin, but we also need to check the diameter because we might have bearing stress failure by punching out through that tie rod on the back end, right? So back up to my picture here. What do I mean by that? Well, if this thing is being pulled, that means that there's, some load from the pin that's being applied to the hole there as well on the other side if this thing is in equilibrium. And if this ends up being like very, very large, you could have that second type of failure, which I talked about in class, which is kind of like this punching out, sort of along these lines, right? Along that sort of region where the pin rips through that aluminum and punches out through that bearing stress type failure. Okay, so let's see if we can sketch ourselves like a little picture of that and determine, all right, forget about the diameter required so that the pin doesn't fail in shear. We probably have a certain limitation in the diameter here so that we don't also fail by bearing stress. So I'll say here, bearing stress also influences the variable d. So we need to check what minimum diameter we need so that we don't fail by bearing stress as well. So let's sketch a little picture of this. All right. So in this case, we have, again, our tie rod. And we're coming up to our little hole location. And here's our hole. And so again, like I said, if we have 125 kilonewtons acting here, then we're also going to end up having from, the pin acting on the structure, 125 kilonewtons as well to balance this thing out. And that might mean that this thing sort of punches through and breaks this guy along that sort of line. And so what becomes influential here is if I were to sort of like draw the way that I sort of drew it in class today, is that you're looking at something that looks like this. And the projected area over which this 125 kilonewtons acts is this projected area here, right? So 125 kilonewtons are acting on this guy, which is looking at this thing if I were to sort of cut this tie rod right here, right? And look at it sort of in this general view. So the dimensions here, this is 20 millimeters. This was given to us in the problem, this sort of dimension here. And this dimension is the dimension D, right? It's the diameter of the hole. So if I'm thinking about the bearing stress, we have a max bearing stress of 250 MPa. And generally, the equation for the bearing stress is going to be something like the load. I'll call it F, or you can call it P. I think we've been calling it P in class. We'll try to stick with that. Divided by this projected cross-sectional area here, which is 20 millimeters times D. I'll just write it as P over A. And I know this is 125 kilonewtons divided by my 20 millimeters for the thickness of the tie rod multiplied by the diameter D. So all this together, since 250 MPa is the bearing stress here, you could calculate what's the minimum diameter required so that we don't fail in bearing stress. And in this case, the minimum diameter required so we don't fail in bearing stress is 25 millimeters. All right. So I have two different values of D that I need to compare. Here is the minimum diameter that I need so that I don't fail in bearing stress. And then up here, this is the minimum diameter that I need so that my pin doesn't fail in shear. And again, that's this kind of idea here. I keep saying pin, but it's a bolt in the problem, but I think of it as a pin. And so we have these two values that we need to select from. A value of D that comes from the pin failing in shear, and a value of D that comes from the bearing stress. And if we're thinking about what's the minimum value, then we have to pick the larger value of the two. So what that means is we need, so the shear in the pin is limiting factor. Since D must be at least 28.2 millimeters. So that's sort of your answer for that variable D. Cool? Cool. One last dimension that we need to concern ourselves with, and that last dimension is all the way back up here. It's the tie rod diameter right where the hole is. So it's this dimension here, the dimension B. But lastly, we deal with our dimension B. And now I have to think about which of the stresses, the shear stress, the bearing stress, the axial stress, is going to drive my choice of this tie rod diameter B. And in this case, we need axial stress. Or I should say we have an axial stress limitation. And let me explain why that is if I cut the tie rod sort of in the middle where that dimension B is. So here I'm going to sort of look at sort of cutting right here and make a free body diagram in sort of that three-dimensional scape, like landscape. It's kind of the same picture that I drew before. But now I can sort of see my dimensions a little bit better. I have 125 kilonewtons that I know is pressing against this back face. 125 kilonewtons. And the internal structure of the tie rod must also balance that out, right? So internally, you have a lot of these little forces that are holding on to sort of balance that 125, right? Since that's what we cut through to hold on to that load. And so together, this and this are an axial stress, which looks something like force over cross-sectional area, all right? Now, the cross-sectional area in this case comes from this half of the tie rod and this half of the tie rod, since I sort of cut it in half right where that bolt location is. So here we have our situation of this being a force divided by a cross-sectional area. And the question is, what is our cross-sectional area? Well, in this case, my force is 125 kilonewtons. And what's the cross-sectional area? Well, let's look at some of the dimensions over here. I know this to be the dimension D, the diameter of the hole or the diameter of the pin that we're going to use. And then I know this full dimension here to be the dimension little b. Sort of the thickness of this particular guy, this is the dimension T, which I know is 20 millimeters. And so when I think about how am I going to calculate this cross-sectional area, well, I can just come up with a formula for that. And that is sort of the width here, or the thickness of the page, 20 millimeters, so 0.02 meters, times sort of this length and this length together, which is the variable b minus the variable d. So should be pretty simple there. Okay, so that's going to give me like the full area here for this calculation. All right, I think have I been saying 67.5? Man, I'm bad at math. These should all be 62.5. Oh, that makes me feel bad. Sorry about this late correction here. Math is hard. All right. Sorry about that. All right. Either way, this is the setup. I know that this is, I'm going to place in here max axial stress. And I know that to be 175 MPa. That was given in the problem. And so I can put these two things together and solve. Since I'm going to force D to be the minimum diameter that we needed in a previous portion of the problem, which is that 28.2 millimeters. And then I can go ahead and solve this. And so I solve, and I'll find that the variable B must be equal to 63.9 millimeters. All right, so pretty complicated example. That was, I think, much longer than I anticipated. But I really wanted to go through that pretty slowly to show all of the complexity that can arise in just what looks like a simple sort of tie bar. All right. I'm going to move on and do the next example. And this next example is stress on an oblique face. Okay, so this comes from slide 10. I'm going to go ahead and copy the problem here. This works. Oh, I didn't get the text. Okay, so here we go. New problem. This is the second example problem from slide 10. Two pieces of lumber glued together at a 30-degree angle, as you can see there. The load P is 11 kilonewtons. Determine the shear normal stress on the oblique face. Okay, so this is kind of information related to the last sort of bit of lecture that we were talking about today. All right, this one's much more straightforward than the last example problem. So what I'm actually going to do is I'm going to do a free body diagram of this with the cut. So that's this cut. And I'm actually going to view it from kind of from the backside. So if I think about like eyeball, I'm going to sort of view it from the backside. So if you thought about taking this piece and kind of rotating it around, you're going to see a free body diagram that looks more like this. And I'm drawing it this way because this is kind of the way that we drew it in a lecture today. Okay. So we got our load P, which is a known load of 11 kilonewtons. And then in order for equilibrium to hold, I would have to have sort of a load that exists along that x-axis equal and opposite, which here would be 11 kilonewtons. This is required for equilibrium. But I know I can break this 11 kilonewtons up into some amount or some component of load that is perpendicular to the plane and some amount of load that is parallel to the plane. So let's go ahead and do that here. Maybe I'll use blue and I'll use purple to show those two different things. But here I have some amount that is going to be perpendicular to the plane and some amount that is going to be parallel to the plane. This is not maybe the best image here, so maybe I'll switch my my red to draw it back just a little bit. Okay, so this 11 kilonewtons is the 11 kilonewtons that's required for equilibrium. All right, so this blue portion here, this is normal to the face. And this here is the variable n, I will call it. And then this guy here, this is parallel to face. And usually we use the variable capital V because that is a sort of a shear force that's moving across that new plane that we created. All right, now importantly here, I haven't really put in my my angle. So let's make sure we get our angle in there correctly. And our angle for this particular problem is the angle theta, which is here, 30 degrees. All right, wonderful. When we defined all the things that we did in class, we defined our angle theta as the angle from the vertical. Okay, so I'll pull this in here quickly just as a reminder, is that when we did all this in class, we defined that angle theta, which you sort of see here, as the angle from the vertical. Okay? And that led us to all these sines and cosines being what they were. In this particular case, our angle here is defined not from the vertical, but from the horizontal. So here, .30 degrees is from the horizontal. So if you want to use the definitions exactly as we wrote them from class, you would need to make sort of a substitution that the angle theta that we really care about, which is 90 degrees minus 30 degrees in this case, which is 60 degrees. And that actually is kind of running out of colors here, but that is this angle here, 60 degrees. All right, so that's the angle from the vertical, which is how I defined everything in class today with that angle from the vertical. All right. So then we have the normal force N, as defined from class today, is kind of this P cosine 60, P cosine theta, which here is 11 kilonewtons, times cosine theta, which is cosine 60. So the force normal to the oblique cut that we made is 5.5 kilonewtons. Could do the same thing with the shear. Our shear force. This is P sine 30. Here's 11 kilonewtons times sine. Sorry, not 30, 60 degrees, because we're using the modified angle theta. And punch this in your calculator, 9.53 kilonewtons. Okay. So these are the values of the normal force and the shear force. Right. We're almost ready to do our stress calculations, but we also have to consider the modified area that we created. So when you do this cut, the original cross-sectional area that we have, if you look at this rectangular cross-section here, I'm going to call this the original cross-sectional area A naught. It's 75 millimeters by 150 millimeters. And when we make this oblique cut, right, so this guy is going to be kind of at an angle here, right? This area is larger. And I'm going to call this A theta. This is the oblique area A theta that we created. And we learned in class today that if we want to calculate that oblique area, A theta, that is the original cross-sectional area A naught divided by cosine of theta, where in this case theta is the angle with the vertical, which is our 60 degrees. Okay. The original area A naught is 150 by 75 millimeters. So 150 millimeters times 75 millimeters. And that's divided by my cosine 60, where I have a new modified oblique area, which here is going to be 0.00225 meters. I did it in meters in my solution here, so I guess this would be 22,500 millimeters squared. Or if you want it in meters squared, which is kind of nice, divide by a million. I think that would be right. Sorry, this is off by 1 decimal point. That's better. 2,250 square millimeters. There you go. Okay, so that's your new oblique area. Now we're ready for our stress calculations. Here I'll write it as sigma theta, stress on the oblique face. Yeah, just write it as sigma. This is N on our new modified area, A theta. Okay, so the normal force is 5.5 kilonewtons. Our new modified area is 0.00225 meters squared. So that means that my normal stress here, this is 2.44 MPa. Again, pressure units, megapascals, mega meaning 10 to the 6th. So 2.44 million pascals. And then shear, follow a similar process. You can punch all those values in yourself, 4.24 MPa. All right, so there you go. 2 example problems. Took a little bit longer than I expected, so apologies for that, but hopefully this is useful. Like I said, this oblique stress problem is very similar to number 3 on your homework. And then the bearing stress, shear stress, axial stress example that I did first is very similar to number 4 on your homework. So good luck with those. I'll be around this weekend if people want to email me and maybe meet on Teams and ask questions. So good luck with it. Let me know if you have any questions. So long for now.